In this video, I will be explaining Hammond encoding for 1511 binary code and syndrome decoding for a Hammond 7.4 code. So this is the final to my coding theory class. And I'm being asked to do two things. Being asked to describe a decoding algorithm, which I'm going to do second. Right, that's this right here. And then before that, I'm going to describe an encoding algorithm, which is just more of a practical side of what we've been doing. Okay, so for this video, what I wanted to do is I wanted to focus on the codes we've studied and its general concepts started in more basic ways. So at some point, all of this was kind of contrived for really, really practical reason, and I would like to go back to kind of those reasons in order to understand these in maybe a little bit better of a way. So what I wanted to do, my goal for this entire thing was to explain kind of the basics of coding theory in a way that I would have understood at the beginning of this semester with no knowledge of this whatsoever. So really, I want to create a start that might help people kind of get back into it, right? That's kind of the goal. So what I want to do first is I want to explain some kind of encoding algorithm. But before they do that, I just want to remind us kind of what's actually happening in coding theory. So what happens is that we have some sender, we're going to send a message, and in some way, shape, or form, that message is going to be translated into some kind of code. In what we're talking about a binary code, so we're just dealing with a bunch of zeros and ones, and that's going to go to some kind of an encoder. And that encoder is going to make sure that that code and any redundancy it needs is going to be able to cross some channel with noise that might flip certain bits of our code. It will get to a decoder, which will correct those bits, and then it will be at the receiver, which will hopefully get the message that was intended by the sender. That's the goal. What I'm trying to ask is, how is a message encoded in this way? Okay. And when doing this, I'm going to be focusing on a Hammond 1511 code. And what this means, which will be a little bit more apparent here in a second, is that our message length is 11 bits, but we have a total of 15. So we have 4 parity check bits. Okay, so let's say I have this 11-bit message that I want to send. I can't just send an 11-bit message, otherwise this channel will corrupt that message in a way that I wouldn't be able to decode, right? So I can't just send the message because one of those bits might be flipped in the process, and then there's no way to recover any of that message. It's basically just lost with no check in order to decode it. Okay, so in order to make sure that that message gets to the decoder and the receiver in a way that it can be decoded into the correct message, there has to be some sort of redundancy. And those redundancy bits that are added to the message, those ensure that. And those are called parity bits. And basically, those are counting different parts of the code and putting it in some kind of code word so that when it gets to a decoder, it knows the counts of different bits in different places. So the Hammond code is going to use the following algorithm to encode its message. Keep in mind that this is 11-bit, and this is also just Hammond. This is a binary Hammond code, so this doesn't apply to every single thing, but these were the basics for these things to start in order to get to read Solomon codes, read Mueller codes, BCH codes, BHC codes, and all that stuff, right? So this is the foundation of this stuff. Okay. So the Hammond Q Code uses this following algorithm. And the main concept here is that one change within our entire message can be perceived in 1 bit. Okay, so even if you have like 256-bit encoding, where your message is 200 and something bits long, if one of those bits changes anywhere, 1 parity bit will find it, right? So let's kind of see this in action, right? So let's say we want to send this message, right? This is our 11-bit message. This means something. It could mean a color. It could mean a letter. It could mean a number. It means something. but we want to be able to send this across the channel without it being corrupted. What we're going to do is we're going to place these bits in these boxes like so, right? So our first bit is going to go here. That's going to be 1, and then 1, 0, 1, 0, 1, 1, and then we have 1, 0, 1, 0 left over. Okay, so this is our message, and we're going to place them in these boxes. Now, these boxes do have meaning. These boxes are counting up to 15 in binary, right? So you can see in the bottom kind of parts of these, 0, 0, 0, 0, that's 0, 0, 0, 0, 1, that's box 1, 0, 0, 1, 0 is box 2, and so on and so forth, all the way up until 15. And these are going to matter a whole lot here in a second. But what this encoding algorithm is going to do is it's going to keep these boxes as parity bits. Again, those are like check bits. They're going to be counting later on. And what this first parity bit, we're ignoring this one for a second. What this first parity bit is going to do is it's going to count non-zero bits with a 1 in the 2 to the 0 spot, right? So again, when counting in binary, that first position, that's 2 to the 0, right? So it's going to count this box, and this box, and then it's going to count these boxes on the right. So we're essentially just counting the even number of columns, and we're going to make that mod 2. Okay, so we're going to add 1 plus 1 plus 1 plus 1. That adds up to 4, which is 0 mod 2. So this box, this part of the message would be 0. This parity bit is going to count numbers, or it's going to count the non-zero. It's going to count the boxes with non-zeros with whatever has a 1 in the 2 to the first position. All right, so it's going to count this box, and this box, as well as these boxes on the right. All right, so if we count that up, we get 2 in that third column, plus 3 in the fourth column, that's 5. 5 is 1 mod 2. So there will be a 1 in this box right here. And then we're going to do kind of the same thing on these boxes, right? Where this parity bit is going to count everything with a 2 squared position, right? So it's going to count this box, and this box. And then it's going to count these boxes down here, right? So it's going to count the second row and the fourth row, so the even rows. So if we count those up, we get 1, 2, 3, and 4. 4 is 0 mod 2. So there'll be a 0 in this part of the message. And then kind of similar to the red parity bit, this parity bit is going to count these bottom 2 rows, right? So it's going to count everything with a 1 in the 2 cubed position, right? So it's going to count those boxes, that third row, and then it's going to count everything in the fourth row. Can't see that, but that's there, right? So if we add those together, we get 4. 4 again is 0 mod 2. So that'll be a 0 in this part of the message. And then our last one, the one we ignored at the get-go, that counts everything, right? So if we just add up all of these boxes, that mod 2 will go in this top left-hand box. So if we add all these up together, we get 2, 4, 6, and 8, right? So everything added together is 8. 8 is 0 mod 2. So there will be a 0 in this box. So if we put all of this together, keep in mind this is just encoding this 11-bit message, our code word is going to be 0011, 0 1 0 1 0 0 1 1 and then 1 0 1 0. So this would be the code word sent in order to send that 11-bit message across some channel and be decoded in a way that would allow us to correct any errors, or correct at least one error and then detect at least two errors. Okay. So that's the algorithm, right? Different bits are counting different numbers of boxes, and then we're adding those together, and those check it for us. Okay, so let's say instead, and I want to make sure I write this right because I erased this before. I believe there should be a 1 right here. Yes, okay. So let's say we have the message down below in red, or in blue, where it's going to be the same as what we just got up here, except we changed this bit, right? So that bit used to be 0. It's this one right here, but we flipped it. So it went across the channel, and that noise corrupted the bit, and it flipped it, right? So now we receive, right? So this would be on the decoding part, but I just want to give an example of how it works, right? So we receive this message. What we do, we plug it into these boxes. So 0 0 1 1 0 1 1 1 0 0 and then 1 0 1 0, right? So we get this box, and what this is going to do is it's going to allow us to check with those parity bits. Okay, so this parity bit, again, is going to be the even numbered columns added together. So that's 1 plus 1 plus 1 plus 1, that's 4. So this is correct. 4 mod 2 is 0, so this parity check box is correct. Right, so there are no errors in the even numbered columns. Those are okay. Then we're going to go to the second parity box. We're going to check that, right? So that's adding together the two columns, right? So 1 plus 1 plus 1, that's 3, 4, 5, and 6. 6 is 0 mod 2. So this is not correct. This tells us that there is going to be an error in one of these two final columns. And then we check the left two, right? So this parity box says to add the even numbered rows together. When we do that, we get 1. That's 3, 4, and 5. 5 is 1 mod 2. So this is incorrect, which tells us that we have an error in this row or this row. And we don't even have to go any further. We could just to check, right? So why don't we do that? If we check that last box, this is adding together the final two rows. That's 4, which is 0 mod 2. So this box is correct. So there's no error in these two rows. And if we put all this together, we know that the only place that we could have an error is in this box right here. Right, so what we would do is we detected it, and all we need to do is flip that bit, which would be along the lines of adding some kind of vector. And then we detected and then corrected our message. Right, so then we would change this to the correct message, and everything would be okay. Okay, so that's the encoding process, and that's what's actually happening on a really practical level, right? So there's some message, and then there are some parity bits. There's those check bits in order to make sure that the message that's sent is able to be decoded correctly into the message that we want to give. Okay, so that's the encoding part. Now I want to talk a little bit more about the decoding algorithm. Okay, and there's a whole bunch of these out there. Again, I'm focusing on a binary Hammond code because these can be kind of generalized later on. And specifically right now, we are talking about the 7/4 Hammond code. Right, so again, this would mean that there are 8 total bits being sent, right? There's the 1 overall parity check, then there's the 7 total, and 4 of those are the actual message, which again, if you just remember what we did above, it's very, very similar, right? So some definitions, for some NK code, right? N is the block length and K is the dimension. For that code C, there's a generator matrix G whose rows form a basis for this code. And this G is an N by K matrix. All this means is that we have some N by K matrix whose rows essentially just make up our entire code. And if they don't show up in that matrix, any linear combination of the rows, so if you add the 2 rows together, you're going to get another code word in our code, right? So for any 2 vectors in C, adding those two things together also is in C. Given this, there's also an N minus K by N matrix for which C is composed of any vector X in our alphabet, right? That's this thing. That's our alphabet. It's base Q and N block length. For any X in this alphabet, if we take H times X transpose, we're going to get 0. In this H, that's called the parity check matrix. And that's going to be really important for our decoding algorithm right now. And for G, if G takes the form, the identity matrix by K, and then the rest of our matrix, H, our parity check matrix, is negative A transpose, and then the identity matrix of N minus K. And that's going to make a little bit more sense here in a second, if you don't know what those things mean. So from our definition of a parity check matrix, we get like the most important thing for this syndrome decoding. And that is that any code word, the transpose of that at least, times our parity check matrix is going to be 0 if and only if that code word is in C. And that's a really, really powerful statement. So basically that's saying that any product of a code word and our parity check matrix is going to be 0. Okay. This product for any vector in our alphabet times our parity check matrix is called the syndrome of X. Right. So that's going to be just a function now where we're just taking whatever vector in our alphabet and we're multiplying it by our parity check, and then that's called the syndrome. And what this syndrome decoding algorithm takes, it takes a vector, which I'm going to call X tilde, which is going to be some code word in C, plus some error vector, and multiplies it by the parity check matrix. And what this is doing is it's checking to see if that X tilde, right, the received message, is actually a code word, or it needs to be decoded, right? So if the syndrome of X tilde is 0, then there is no error. And so X tilde is in C and that message is valid. If it does not equal 0, then it's going to point to the position of the corrupted bit and it's going to be able to flip it for us. Okay, so this is where it gets interesting because there's a lot of information here. Okay, I know what I did wrong. This column shouldn't be there, which makes way more sense. All right, so then our parity check matrix is almost correct. We get 0, 1, 1, 1, 1, 0, 1, 1, and then 1, 1, 0, 1. And then we're going to get the identity matrix. That's 3 by 3. So we get 1, 0, 0, 0, 1, 0, and then 0, 0, 1. Right? So this is going to be our parity check matrix. And basically what happens is if we take any of these code words, x0 to x15, if we multiply it by this parity check matrix, we're going to get 0. Okay? So just as an example, like let's take x2. So if we take h times x2 transpose, we have our parity check matrix, times x2 then we multiply rows by columns. This is just multiplying matrices together. So we get 0 times 0, that's 0. Another 0. 1 times 1 is 1. Plus 0. Plus another 1. And then plus 2 zeros. Right, so we get 2, which in base 2 is just going to be 0. Right, that's our first row. Then we do the same thing. So we do 1 times 0, that's 0. Another 0, we get a 1. We get another 0. Another 0. Another 1 and another 0. So then we also get 0. And we're going to get 0 for the remaining. Right? You can check that, but we're just multiplying these two matrices together. And we're going to get this 0 vector. And what this tells us, this equals 0. Therefore, this x2 is a valid code word, which we already know because we have it up here. Again, they're just linear combinations of any row in our generator matrix G. Okay, so we get this. Okay, let's say instead we're talking about x11. So x11 is 1 0 1 1 0 1 0, and let's say instead of getting x11, we flip one of these bits. Right, so in this case, we are flipping this bit. If we do this, we're going to get an error because that's not a valid code word. Okay, so we do 0 times 0. That's 0, plus another 0, plus 1, plus 0, 0, and then 2 zeros. So we just get a 1 in this place. Then we do the same thing. We do 1 times 1, that's 1, plus 0, plus another 1, 0, 0, 1, and then another 0. So we get a 1 again. I think we had 3. Okay, so 3 mod 2 is just going to be 1. And then we do the same thing again. 1 times 1 is 1, plus 0, plus 0, plus another 0, zeros, and more zeros. So we get 1 plus 1. Actually, we just get all 1s. Yeah, because 1 times 1 is 1, and that's the only one we get. So that summed together with nothing is just 1. So we get this vector of 1, 1, 1. And what this does, this is not equal to 0. Therefore, this code word is not it's not a valid code word, and there's an error. In order to check this error, we look at the column corresponding to this vector in our parity check matrix. And this is column 4, which means that in the 4th bit, we have an error. And then all we have to do is add a vector, right? So we would add or subtract, and I guess in this case it doesn't matter because it's in binary. Right, so that's what we received. And then we would just add a vector with all zeros except for that 4th spot. And then we would get our original code message, which is 101, 1010. And then that's the decoding algorithm, right? So what we do is we multiply what we get by our parity check matrix, and what we get is some vector. If that vector is not 0, it corresponds to some column in our parity check matrix, and that tells us the position of the incorrect bit. And then all we have to do is we have to add a vector with just a 1 in that bit place, and then we get our code word. Okay, so that is the decoding algorithm. I think that took a little bit longer than I intended, but that's the algorithm and that's how it's done. So thank you for watching, and I will see you next time.